So, in your refinement process and in your influences, this is where you would find this information. Your design process for building your robot. You know, this is just a basic thing we should all be teaching in tech ed classes. You know, what your design process is, define the problem, gather information, generate solutions, analyze them, test them, and implement them. So, you know, pretty basic. What problem do you need to solve? Well, you need to survive into your campground. That's your basic goal. Survive the competition and document how you survive. One example I have is we designed a robot down in Cal. We went through a similar design process on this robot. What it does is it climbs up and down a rope, and it has a video camera on it, transmits real-time data wirelessly back to a screen. And we did it for the Earth Science Department because they wanted to show students the rock strata of a rock face without actually having to take all their students over the side of the cliff. You know, you got like 25 people on a rope. It doesn't work out so well. So send this little 5-pound robot down, and they can show the students all the stuff without putting the students in harm's way. So that was our problem that we defined. How do we show the students the rock strata without actually putting the students in harm's way? For you, how do we destroy the other robot without being destroyed ourselves? You know, go out. I realize I say Google a lot. Google it, check it out. Google, awesome. If you have some other search engine you like, go for it. But always go out and search out similar solutions. What we looked at for going up and down the road, we really didn't find anything out there, so we had to come up with something. How do we do this? We figured 2 motors, 2 sets of wheels that can grab the rope and drive itself up and down. Pretty simple design. Worked out pretty good. Actually goes up and down. And I brought the binder to show the documentation behind that robot, so you can see like an applied application. When you're out doing research, looking around, Googling things, look for weaknesses in other designs. If you're watching this video back here and you see a robot get ripped apart, you know, look at it and go, why did that fail? Why did it get ripped apart? How can we learn from that? What did they do that we can do differently that we won't get ripped apart in that situation? It's very important. Let's see. More solutions is more better. I like that. Kind of grabs attention. Lab goes. Yeah.
He is a college.
I got 2.5 college. And I still use horrible grammar. In the beginning, every idea you can think of, whether or not, I don't know if you've competed in the VEX challenge at Cal U before. You know how they put on their website a detailed video of how the challenge is played, and they make robots that you can never make with VEX parts that levitate and fly, and they have these like anti-gravity guns doing crazy things. No idea is bad in the beginning. This is the time for creativity. Every idea you can think of, be it something so off the wall that you can never actually get it to work, still put it down, because you might find something in there that might actually work in your final design. There's no bad ideas at this point, but that can be like a subjective kind of thing. Alright, so you selected a solution. Took all those crazy ideas of levitating robots and robots that have cloaking devices so the other team can't see you. And you can hit them, they don't have a clue what happened. Remember, you gotta build it. You can draw anything on a computer, it'll all bolt together on the computer. But when you actually go to build in real life, you might find that, whoa, you can't actually get a screwdriver on that. Or on that screw inside the middle of that chassis because there's a other chassis row in the way. Or you might find that you pulled the tolerances so tight you can't get to that screw. You might be able to build it and get that screw in, but whenever you go to work on it, whenever it takes a massive blow and something gets sheared, you go in there and get that bolt. You might not be able to get it. You might have to disassemble half the robot to get that bolt out so you can change that part. That's not exactly what you want to have happen in that very time-sensitive competition in BotsIQ, where you can be up at a minimum of 20 minutes apart. You want to keep that in mind. You got to be able to tear this robot apart, rip half of its guts out, and get it back together in 20 minutes, put it back into your and go fight again. And that's an important part of analyzing your designs and picking the final solution that you're going to use.
We lost the competition because of we could not get our bot back together in 20 minutes. It was a simple belt. Snap the belt.
Prime example.
Snap the belt. All we had to do was put a new belt on. We had it there, but our team could not get the bot apart and back together in 20 minutes. And we forfeited.
All right. After you get it designed and built, try to get it done, not the night before, because you can't drive. Driving is important. You can have the best robot in the world, but if you can't drive it effectively, the other team's going to beat you with a far lesser robot. It's happened plenty of times, and it's happened for me at Cal with robots when we do the VEX competition. We went to Dallas this last year, we beat internationally on that challenge, and we had serviceability issues where we didn't follow the motto of how do you fix it in less than 20 minutes. We didn't follow that, so we got hurt on that on multiple occasions. And the driving issue. We didn't drive our robots enough, so we weren't skilled enough at driving them to compete highly effectively, even though we had very effective designs that could complete the challenge like no tomorrow. They were excellent, but we couldn't operate them effectively to use that excellence against the other team. Same thing here. Your robots are going to probably be tiny and super fast, and your weapon might take a little while to spool up, so you need to know how long that takes by practicing. You need to be able to control the robot in there. And it's one thing to go after a stationary target. It's an entirely different thing to go after a moving target. Trying to come in contact with something when you're usually, you're driving down the road, you're trying to avoid contact. You're always trying to get away from the other guys. This time you're driving in this arena, you got to hit the other guy. And that becomes complex whenever the little robot screams around really fast. And your little robot might be a little bit twitchy. You have to practice. And that's a major part of getting the robot done early and being able to practice with it. You get it done the day before, you can only practice for like 12 hours all the way through the night. You get it done 3 weeks before, I don't even know how many hours that is. That's a long time. You should be experts.
Mike,
Yes, sir.
one thing about driving, one thing that a lot of teachers kind of overlook is they think they need to have their whole robot complete to drive it. If your drive train is done, drive it. How many matches were you in there the weapon puts work? You have to drive. So even if there's not a weapon done, a weapon's not on it, let the kid drive it. Let them drive it. And the other thing about driving too, most motors that you're going to use, whenever you first get them, they need broke in. You don't be able to take a fresh motor and throw it right in a battle. It'll wear the contacts out a lot quicker. We went to a lot of different competitions, and you've seen teams running their batteries down for 2 hours, and the motor constantly running at a certain speed for 2 hours long just to get their contacts to work. And that's something that you want to do. You want to break your motors in. It's the best way to do it. Let them drive it without the weapon on. Even if it's not done, whatever. Get the drivetrain done first, frames done, let them drive away. Little 1-inch movements mean the world.
Another thing we've done is made up an obstacle course in the hallway of our school in time how fast they could go through around an obstacle course, even if it's just a big oval track, and taking the best times there. That normally is showing us our best drivers, and then we give them the first opportunity in the competition. That can be just with the, you could even use a VEX robot for that, just to get the hand-eye coordination, because that is really a talent. It's something almost like an athletic sport, having that ability to have that hand-eye coordination And then it's totally different when you get in competition, I'm sure. But at least that gives you your top 2 or 3 drivers of who you can start out with there.
Absolutely. And everything that we've been talking about here would go in your testing results section. So we tested the robot, who was driving it, who drove it the fastest. So that's how you determine who was going to drive it.
Yeah, we would do the same thing. We would have a little driving competition with you had to do certain requirements in time. We added one thing, we would have the rest of the team scream at the person while they were doing it. And we actually had one of our drivers, just hand the controller off. He said, I can't do this with people yelling at me. Well, of course he wouldn't be able to do it in competition then because everybody's yelling at you.
Another thing too is, whenever you get closer to competition, the kids always want to drive. I need practice drive. I need practice drive. So what they'll do is they'll run the thing full throttle down a hallway or whatever, and wherever they're doing it, even if they take a weapon on. Don't go full throttle. The ESCs heat up. We've had a kid, the night before the competition, weapon ESC's out, all right, you can drive, and then ESC's blunt because full throttle, full time, 5 minutes long, it's going to get hot. The IC's going to move on you. You know what I mean? So try to keep it to where they're not going long distances or they're not going full throttle over a long period of time. Shorten it 2 minutes maybe. Not over 3, definitely not over 3.
2-3 minutes, leave them cool down because you can burn out components real quick, overheating the motors or the speed controllers. And leave them cool down twice as long as what you run them. And have somebody with a stopwatch your time as they're running.
Yeah. If you feel, put your hand not on the actual components, but next to them, and you can't keep it there, you're definitely way too hot. You don't even have to go based on time. If you can feel heat coming out of the robot, just let it sit cool. Sometimes even running it for a short amount of time, if something's not quite right in the wiring system, something will heat up super hot, and you might not necessarily catch it. Or if you only go for 2 minutes and you let it sit for 4, it might not be cool enough. Actually get your hand by it, but don't touch it. Just burn yourself because on motors before. It doesn't feel good.
Hey, another thing, a lot of times before the competition, a week or 2 before, they'll set the arena up. Last year they had to set up the science center, and that's a great opportunity for your new drivers to get in there, and they'll throw an old computer in there or a chunk of aluminum in there and see what they can do under in the actual arena itself. We learned a lot last year.
No chunks of metal anymore, unless they're super heavy. One got thrown really hard into the side of the arena. Not doing the small chunks of metal anymore.
Well, driving.
You can drive, you can throw another robot in, and you guys compete on each other just as you would in the competition. But no small, it turned into too much of a projectile against the arena. Being light, and it could be accelerated really fast. And
You're not pointing fingers now, right?
no, not pointing fingers. Just no small
But
chunks. Now, if you want to put a 30-pound chunk of metal in there and hit it,
I wouldn't recommend that though because you're just going to
you'll hurt yourself on that. But
Guys, one thing with that same topic, 2 years ago we had a kid that was a freshman, and we actually went through a competition, and I think it was science, and we were somewhere in Drove, and this kid came down with the group. Wasn't in a club, didn't help build, but just was kind of interested. The kid threw the controller in his hand while we were practicing, and now he's a junior and he's our team leader. You know what I mean? So just stuff like that, where maybe you don't grab the attention of someone up front in the fall, where in the spring, whenever you start getting these things built, and they're a young kid, don't be afraid to, if you're going to practice somewhere, invite them, maybe throw the controller in their hand, let them drive a little bit. They get hooked. They really do.
I wouldn't be afraid to take a senior on a team either and leave him drive, even if it's his first time. We've had some of our best drivers come in as a senior. They just weren't attracted to it before then, and they've done some of the best driving of anyone. So age doesn't matter. It's just the person, Go with your best drivers. You have a big toolbox. You need all the tools. Use all the tools that you can in this competition because everyone else is going to. So, take advantage of whatever you can, whether it's your company sponsors, your best drivers. fundraising, get as much money as you can, because you can never have too much money in this sport.
Alright. Well, I kinda like that movie Planes, Trains, and Automobiles. Use everyday objects that you might find someplace for your design. Bridge trusses. I love bridge trusses. They're simple. They use triangles to distribute the weight load from side to side. Triangles, you know, whenever you use a box, you can push it to the side. When you have a triangle, you can't push it to the side the way the geometry works out. You know, try to work a bridge truss in your design. Working on a robot down in Cal on Clark's senior project, and everything looks like a bridge truss. The frame that it sits on looks like a truss. The swing arms for that hold the wheels look like a truss. The frame rails look like a truss. Everything looks like a truss. Just crazy. And that's one of the components on his robot. It's going to be made. That's the swing arm. The motor goes through the one end, the other end attaches to the robot, and it's going to have dynamic suspension. We'll be able to raise and lower the robot, kind of like a low-rider car. So whenever it sees something in front of it, it'll be able to raise itself up and go over. Could have about, 11 inches of travel from low position to high position. So it will be rather interesting. But we got the idea for that design from a bridge truss. Don't be afraid to copy off the things that work out in real life. Use simpler is better. The KISS method, keep it simple, student, or student. That doesn't always work because we made this really simple, and that's the robot we built that goes up and down the rope. But as you can see, there's so many bolts that got to go into all the components to hold it together. You see all the spacers that you have to build it in two halves, and should something break, you have to very carefully take it apart. Everything bolts together so hard, it takes like 3 hours to take this thing apart to service it. So we went with a very simple design, very rugged. It goes up and down the rope, no problems, works flawlessly. But should we ever have to fix it out in the field? There is no fixing it in the field. You have to do it in the lab. You have to do it in a workshop. So that's a little bit of experience that I've had with designing robots. And this would be something you would talk about in your refinement section. This is the motor mount for that robot. The motor sits inside here. We drew it on the computer as one solid part originally. Well, turns out that one solid part, we'd have to take like 90% of the material away from a solid chunk of aluminum to make that. And it was going to take multiple processes. It was just going to be so incredibly difficult to manufacture that part. We just decided it wasn't worth the likelihood that we'll scrap 3 or 4 of those before we get a good one. So what we did is we turned it into sections. We made it the front plate out of a piece of plate, back plate out of a piece of plate, and the tube in the center out of a piece of, I think we ended up using round stock. We didn't have a piece of tube that was close to that size. And then welded it all together. Fine. Oh, my favorite part. SDPSI, they have a website, Stock Drive Products Supplier Index is the name of the company. Almost every part they sell on that website, you can get a 3D model of on their website. You can download it. So if you're going to use belts, you can download this belts. If you need gears, drive cogs, bearings, bolts, shoulder bolts, everything that you can think of, you don't have to necessarily draw all the parts for your robot. You can go right on here and download. We do it all the time. It's great. We didn't realize that in the beginning. We drew a lot of our own parts. And then we found out you can just download it, and in like 5 minutes you can have a part that would take you 3 hours to draw because of the way the teeth are on here. It's way awesome. And you can get it in like any format. On your download screen, you can pick Inventor, SolidWorks, EXF, IGS, and IGS is the one I've had the best luck with. For some reason, it works out the best, and you can import it from Inventor into SolidWorks, into Pro Engineer, into anything you can think of that IGS file.
Yeah, Mainbot and those big companies we use offer that.
I don't think
There is there's a website, battlebot.formotion.com. They've got a parts catalog that has
Standard 50 flats, 50s, and
all your stuff, the regular stuff, all my hot
Your
switches,
heads.
and inboards, and outboards.
McMaster Core does a pretty good job on a lot of, like their hardware and things like that too.
And this belt we used in this picture, we used the design accelerator in Inventor. There's under a certain screen. And you can tell it what kind of belt you want to use. You can tell it go around this gear and this gear. And what it does is it'll tell you how long it is, how many teeth, what the actual length would be, and if it's a standard length. Right now, in this design, that's not a standard length, so it shows us, hey, that's not going to work. You can't buy a belt that has 97 teeth on it.
Does it do pitch? Does that do pitch and everything too?
Yes. You can pick different belts over here.
So I'll actually tell your pitch here.
Yeah, you can say you want to use a double-sided MXL belt, and it automatically pulls up what's industry standard, whether it's a 100-tooth belt or a 90-tooth belt.
That
Tells you.
Inventor? That's an Inventor?
That's in Inventor.
I know SolidWorks does it also, but I'm not sure if it tells you the pitch of the teeth and stuff like that. It'll draw it in.
Important whenever you design is to get the spacing center to center on those, because these belts are only available in increments somewhere around 1 inch. You can't get them every quarter inch, half inch. So that's something you want to consider whenever you design your robot, the spacing on wheel centers or weapon to weapon motor mount, so that you can avoid idler pulleys. You definitely don't want to use an idler pulley on a tensioner pulley on a weapon belt due to the RPM. Good luck finding a bearing for that. And your drive belts center to center, if you choose a 4-wheel drive design. That should be at the top of your list. On your prototype that you make up, is to get that so that you don't have to go through tensioners. And we've had to use tensioners already, and the tensioners add weight. You don't want to put weight into things that aren't going to be helping your weapon.
That right there is probably one of the most important aspects of the drive system. What's kind of up there is just center to center distance. And there's online calculators, like if you go to Stock Drive Products, they've got a calculator there for you to say you've got this much distance between your centers, and here's your diameter of your 2 pulleys. What belt do you need?
Yeah. Another thing, when you order your belts, you need spare parts. Order all your belts, including your spares, at one time, because if you get it from a different order in different, they could come through maybe a quarter of an inch difference in size. So if you have a robot that's going to take 2 belts, you want 2 spares, order 4 belts right from the get-go. McMaster Car is pretty good. If they're not the right size, they take returns quite easily. But don't order 2 now and say we'll get 2 later, because we ran into that and they were different in size, and then that messes you up, especially if you don't find out until a competition you have to replace something. So try to order all your parts at one shot.
McMaster Car is very fast. Sometimes you'll get them 2 days later, within 2 days. Econo Belt, we've had some decent success with too. And they have a nice site and everything. They're very helpful.
But the other thing about that too, I mean, you've got geared drives, so you've got your pitch and your teeth and everything. Don't be afraid to flip the belt over. Get rid of the gears. They work just as good, provide a little bit of slippage, which in turn is easier on the motor.
Especially on the weapon.
So get rid of the teeth and just go with the flat side of the belt. Save your motor sometimes.
What we did with this one is we made oval mounting holes on the frame so that we could pull the motor to tension the belt. That's how we got around not quite having the right size. So they're actually ovaled out. You can slide the motor up and down with tension on it. Might not work so well in a combat robot because it'll take a pretty good hit. The motor might slide, so you might not want to do that. but that's how we solved our problem. Weight's a huge issue. Since you only have 15 pounds to work with, and your batteries are probably going to weigh at least 2 pounds, that leaves you with 13 pounds. Cool thing with Inventor is, and any other 3D parametric modeling program, we can set the properties of that chassis. That's part of his robot that we're going to build for the scene project. We found out how much that weighs. We told it we were going to make it out of 60-61 aluminum. Just plug that in, tells us it's going to weigh 3 1/3 pounds. So you'll know how much roughly your robot's going to weigh before you do it. But remember to take into account that you're probably not going to have your battery in here. You know, if you're going to buy it off a website already made, they'll probably tell you how much it weighs. Look at your motors, how much they weigh. Wiring is heavy. You might not think that, but it is. So nuts, absolutely nuts and bolts, they add up very fast. Don't design your robot in the computer to weigh exactly 15 pounds. You know, give yourself some room. You don't build it to 12 pounds, because when you put that wiring in, that's going to take 3 pounds quickly. Yeah. Nuts and bolts, they really add up fast.
Can we ask, how many of you guys are using solid modeling programs for doing this stuff? So the majority? Okay, so you're familiar with these things. Like Mike said, if you're using a battery and there's no setting for battery, you know, what we would do is we would draw a block, the dimensions of our battery, and then we would assign it a weight. We'd weigh the battery and then assign it a weight. These things are surprisingly accurate also. They're pretty darn close to dead on. If you're using, you know, a certain grade aluminum, it's pretty accurate. One thing that you do have to watch, this happened to us, is one of my students was designing a weapon and he had the material picked as like rubber. And so it turned out we had this real nice light robot. Well, it turned, you know, he liked the color black on his weapon, so he picked rubber. And obviously that's a lot lighter than tool steel. So make sure they have the right properties if you're using these models, that they're not using balsa, or you can actually select air too if you like.
So if you guys, if you're using something that you don't know, it won't have the density value for you. Just, you know, whatever we talk a bit later, we're going to show you there's tables you can have, tables you can get that show the density value. That's basically the value that you put in there, the density value.
Just plug it in.
So you just plug it right in there and assign it that value. And the other thing too is, I don't know if you guys have noticed that the SolidWorks is more accurate than Inventor with weights.
Oh, really?
And if you want to get real accurate, spend $20, $25, go on eBay and get a digital scale. It will handle up to 20, 25 pounds or so. That's the bottom line. You have to have a digital scale. You know, don't count. It's not going to lie. You know, you put everything on there at the end, and you're going to see exactly what you have.
The postage scales are very accurate.
Yeah.
If you buy them, be careful though. Some of them stop at 15 pounds.
Yeah, you don't want one that.
So you put your bot on there like, hey, 15 pounds. Right. Yeah, it's actually 35.
You just broke the scale.
If you guys, if you get your electronics in, and you're waiting because something's not finished, weigh the electronics. You know, cut wire, maybe the wire might be a little bit too long for what you're going to need. That just puts you under a little bit more. But weigh all the electronics. That way you take your frame, your weapon, there's one weight, and you got all your electronics going inside. You're going to be close. You know, don't go, like Mike said, don't go and say, okay, it's right at 15. But that's a way that we usually do it. If something's not finished, we'll weigh all the electronics with the wiring and everything already cut to longer length, which gives us a little bit. And then we know if we're close or not.
Good point for robot.
Until you have to reduce the robot by 3 ounces, and the only thing you have to work with is aluminum, you can't appreciate how much aluminum it takes to reduce a robot by 3 ounces. Our first year in competition, we had to add a battery pack because we didn't have enough power. So adding the battery pack put us 3 ounces overweight. Well, we were down there the night before the competition with a 1/2-inch drill. It looked like Swiss cheese. You don't want to turn into that. So that's why another good reason, have your robot done at least a week or 2 ahead of time to make sure that's in order, and also to give your drivers time to drive. You know, if it's over 15, they won't leave you compete. That's it.
And you brought up
Solder is heavy. So if you're weighing your electronics and stuff like that, remember that, you know, Plus, kids love to put way too much solder. So I'll show you some really good examples of it. But yeah, solder's heavy.
All right. So we know how much it's going to weigh. We made a design. We think it's going to be super strong. Is it going to be tough enough to survive the arena? And so this is where SolidWorks comes into play. Tanner's done this a lot. He knows exactly what I'm going to talk about. Probably correct me a little bit here. But the factor of safety on a part whenever you're doing structural analysis is you tell it what kind of material it's going to be made out of. It takes that into account. It takes the actual physical design of the part. And then it looks at how much force you think the part's going to have imparted on it. And it computes all that and it spits out a factor of safety. Factor of safety, 1 means the yield stress of the part is equal to the force you believe will be applied to that part. If it's less than 1, the yield stress is greater than the strength of that part. And so we know with pretty good likelihood that part will fail. And if it's above 1.0, then we know that part should not heal. That's not to say that it won't, but if it's above 1, it should survive. And what SolidWorks will do, you can pick a specific part on a robot. So I was looking at this mounting hole and this mounting hole and trying to determine whether or not they were actually going to be strong enough. Turns out I'm in good shape. I put way more load on than what it ever should see. I put like 75 pounds of load on there. It's never going to see that. So we are good. That's at 1.39. So, yes.
Something that's really important, I don't know if you're going to get to this, with the idea of optimization. So if your number is like 15, you know that the material that you're using with your design is way overkill. So you know that you can sacrifice taking weight off and adding it to another location on the bot where you think would be more appropriate. So if you're getting a number, there it is, optimization is a big part of that.
Absolutely. So if it's like a giant number, like he said, 15 or 20 times, you know the part's way overbuilt, you can go with it if you have the weight to work with. If you don't have the weight to work with, that's a good place to take it out. But more FOS is more better. So greater that number is, the less likely it is to fail.
One thing you guys got to remember whenever giving you the FOS, you know, about a different force than what you're going to get whenever a 20,000 RPM beater comes and hits you. All right, I mean that impact load is a different measurement than what FOS is. So go heavy. And that's kind of my advice. If it says it needs to be 10 and you make it 10, well, you know, whenever pump comes at you with a 20,000 RPM beater and hits you and it bends, you're going to say, why did it bend? And it's usually because you didn't go 20 instead of 10. So beef it up a little bit.
There's some calculators out there on the web too that can, you know, if once you know what Plumb's spinning their weapon at or whatever, you can go out and figure out how many joules of energy that thing's going to hit you with, and then you can plug that in. So you can. There's calculators on the web that you can actually plug some things in.
My kids always think they need to be rocket scientists whenever they look at it.
Yes. Or,
He's a, wow.
transferring power. But you can actually calculate how much force you're gonna undertake. It's a lot. You'd be surprised.
I have a few 3D models that we've worked on in Cal. I gotta show them to you. This here is that Climbot we worked on. And
Is that a banner?
this is Autodesk Inventor. It's a very heavy program, as you can see it bogging my laptop down. You see how it kind of pixelates out and has a little trouble.
Yeah, this is another program too. I mean, I know we mentioned the student version for SolidWorks. Well, They've got a student version for Inventor also.
Yes. And Inventor now has new software. It's called Robotics.
Right.
I forget the exact name of it. Robotics Stress Analysis. And it can take whole assemblies and do a stress analysis on whole assembly. I didn't have time to get that for today.
Single point.
Something else is Inventor also offers student versions for download. So if your kids sign on to the educational community and your school district owns the license to Inventor, they can download at home absolutely free and use it on their home computers.
Does the school district have to own Inventor?
Yeah.
Yes.
Yes.
You as a teacher have a ID number. You as a teacher have to
Set them up.
give them a password, or I think it's a password to do it.
It depends. If your school district has school emails, you don't have to go through the password. But yeah, then they can download anything. And most people that have, usually if you have an architecture class and you have Revit, usually they sell Revit with Inventor because it's the design academy. You might have it, you might not even know it. And if you can get into that educational online community, then you can download copies of it. Kids can download as many as they want.
And that's the actual version I have on this computer.
Yeah.
Because I don't have a full version, I have the student version. Like Jeff said, you can draw out a battery. That's what we have on the side. So we have the actual battery pack to drew it. The only thing that's not in this drawing is the wiring on the robot. And it looks identical to this in real life. The exact same colors, battery packs are black, the parts holding the camera are red, servo's black, aluminum. I mean, it literally looks identical to this in the real application.
Inventor have a PhotoWorks.
Yes.
Yeah.
We can even save this assembly as just a regular JPEG,
Right.
and you can export it that way, and if you can,
SolidWorks will actually take your drawing and raster it so that it almost looks like a photograph. It's pretty nice for portfolios.
SolidWorks is a little bit better.
You like SolidWorks over?
I have both, and I started with Inventor. Inventor is very intuitive and for first-time users. I use it with middle school kids. So Inventor is very good at the beginning stages. SolidWorks, in terms of testing and rendering, in my opinion, is much better.
Right.
Their analysis testing is much
It
better.
is.
Like you said about accuracy, way more accurate. And in terms of renderings, you can do really photorealistic renders on SolidWorks. You can on Inventor, but they're not as nice.
A lot of times what we'll do is we'll use Inventor, and then like the test weight or something like that, we'll bring it into SolidWorks.
Import it in. And that IGES file is good that you import it with, and so does Step.
Yeah,
STEP.
Step's an open
Step,
source.
Step's the other one.
I'm pretty sure the machines companies, the NC equipment they want an IGES file.
Yeah.
So you want to check with whoever's going to do your machine
Right.
what file they want, so that they don't have to be converting. You have anything else on model, Mike, or not?
I have two other models. If you
I was
want.
just going to throw in what I had before we finish
If you want
up.
to throw in, go for it.
What we have done, and it's really helped out in the past, is to take even after you design it and everything looks like it's going to work, we'll take and we started cutting these out of in the wood shop, and then we went to using a legend engraver laser to burn these out. But this is a great way before you start cutting metal, is to make it up out of wood and make sure that all your components are going to fit, and if things are going to work the way they're supposed to work. Because many times we have to redesign these, and it's a whole lot cheaper to cut wood than it is to cut metal. And I would want to go to one of your industrial people and say, hey, we need another ½ inch here or there, because that's big time money. We have to do that. If you have a laser, this is only about a 30-watt laser engraver. It'll cut through ½ inch hardwood, and we could burn out this entire chassis probably within 10-15 minutes. You try to do that in the wood shop, it's going to take you longer. It can be done, but it's just going to take you more time. But I would strongly recommend. We started out making cardboard prototypes, and then we got into the wood ones. And each time before we went to the final design, we ended up making up a wooden mock-up like this here. My kids have been real stingy because they don't want to waste weight for space. So a lot of times they get too tight. You got to keep in mind, you get down to the final runs, you have somewhere around 15 or 20 minutes to swap out a weapon motor, a drive motor, a belt. So you have to make things accessible so that you can take and swap these things out real quick. That's something you really have to consider in your design. Also, you need accessibility. Any set screws that you have. Our first year with the original Shockwave, we were up against Jeff, and the set screw worked loose, and we didn't have access to it. And we couldn't get to it in the amount of time, in 15 minutes to tighten it up, so we had to go without a weapon. Well, that's the last time that ever happened. All it required is drilling a hole down through. I'll show you some pictures later. They have a hole so you can put an Allen wrench down there to take and tighten that set screw. So little things that will save you a lot of aggravation and maybe get you a championship someday. I strongly recommend prototypes, whether they be wood or cardboard. If you have access to an engraver, it's a real easy way to make up a prototype.
There's a lot of little tricks that you could do. You know, my rule was never use set screws, but you always have to. You know, so even though I say never, you always have to somewhere along the line use a set screw. So a lot of kids and teams will just use a set screw, as in a single one. I'm thinking, well, if I put two in there, it shouldn't work loose. You know, so it's just those little things where, okay, I'm just going to put two set screws, it's not going to come loose. You got less of a chance of it coming loose. Just those little things like that will cause you a match. Those little pieces of information are the key ones that you really got to look for.
Anytime you can use a Torx head versus a socket head, or what we refer to as an Allen head, to do that. It's a lot easier, less chance of stripping. When you go into a competition, have your wrenches identified. If it's a T15, T20, T25, color code them so that there's no mixing up and stripping out the head on it. Allen heads are a lot tougher to use, but sometimes you have to use them, like Rick said. You have to use those Allen heads. They have Allen heads that have Loctite built into them. Torx is definitely the way to go. You never want to take and put a button head or an oval head on the outer perimeter of your robot, because trust me, they'll take right off. Jeff took our tensioner screws right off the sidebar. They just went flying like popcorn. So you always want to use a flat head, keep it flush with the surface, because probably sooner than later you're going to get a spinner that's going to come up and start taking those heads off. So on the outer perimeter, inside it's okay to use a button head or a round head, but on the outside, keep everything smooth and flat. Not only does it look better, but it's a whole lot more effective.
You might luck out the first time with someone not take that button head off, but it'll eventually get taken off, and then you have to go and get the vice grips out and actually take everything off, and then take that bolt out because it's snapped, and it's just, you only got 15 minutes, and those things add up quick.